Last time at the end we stated this lemma 154, and today I want to look into proving it. So the setup is this same sort of very minimal setup that we've been looking at. You have fancy A being any collection of sets, any collection of subsets of x that contains x, and mu any non-negative function. Then mu star, the outer measure induced by mu, is countably subadditive. So this outer measure thing, mu star, is a very robust construction. You can start with pretty much garbage, and it will give you something at least countably subadditive. And remember, at the end last time, we talked about also the bad news. So this is the good news, but the bad news is that it's really quite hard to prove countable additivity. You're not going to have countable additivity in just any situation, even if mu starts out countably additive. We will find that part of the reason for this is that mu star only carries any nice properties that mu might have so far. So mu star is actually defined on the entire power set of x, right? Like, you can feed it literally any set. Any subset of x, you can take the outer measure, and that will be some real number. But it's not necessarily going to have good properties on all subsets of x. It's not necessarily going to preserve any good properties that mu might have had on all subsets of x. This is why we introduced this idea of mu measurability. So given mu and this fancy set A, which is its domain, then we've defined this collection of so-called mu measurable sets. These will be the ones that we will find mu star behaves nicely on, assuming mu behaves nicely to begin with. So what's interesting, I think, about this lemma is that you're getting countable subadditivity with an emphasis on sub, which is the best you can get, but you're getting countable subadditivity of the full outer measure, the full mu star on all of the power set of x. So on this entire giant thing, you're getting this property. It's quite a wide-reaching result. Now, before we start this proof, since it's been a couple of days, I want to remind you about the definition of mu star, and I think I can also create some notation that maybe makes it easier to talk things through in a sort of talked through and not only written proof. And I also want to remind you the definition of countably subadditive, since we did make a small modification to that definition, and it has been a little while. So let's start with that. The definition of countably subadditive is this. So if you have any non-negative function, let's call it nu, just to not confuse it with previous things. If you have any non-negative function nu on any collection of sets, really, then we say it's countably subadditive if and only if whenever you have a countable family of special sets, things in your class of sets, such that the series converges. So this is how we modify the definition a little bit. If you have a countable family such that the series converges, and such that the union is also in there. Remember, this does not have to be a sigma algebra. It could even be just like a semi-algebra or just some random collection of sets. Then in that situation, we have that nu of the union is bounded above by the sum of the nus. So the subadditivity, the sub part of subadditive, you should think is this inequality. That's the subadditivity. Additivity would be if you had an equality in situations where these were also assumed to be disjoint, pairwise disjoint. Subadditivity, inequality, and also you don't need to assume they're pairwise disjoint anymore. And things to watch out for that are sort of subtleties of the definition are basically the definition is saying you have this whenever both sides make sense. So you only have to check situations where both sides make sense. So this has to make sense, meaning that you have to be able to apply nu to this union. So that's why we're requiring that the union be in your original class of sets. And this has to make sense, meaning the series has to converge. If you do things using the extended real numbers, where you allow the series to take the value infinity, then you don't have to talk about this, whether this makes sense or not. It always makes sense, since it's a series of positive numbers. So it's the limit of a sequence of partial sums, which is a monotone increasing sequence. If you allow for extended real numbers, then every monotone increasing sequence converges. It either converges because it's bounded, so it converges by the monotone convergence theorem, or it converges to infinity because it's unbounded and increasing. Okay, but for us, we don't want to talk about converging to infinity. Now, next I want to give you the definition of mu star again. So here's our definition. For any subset B of x, actually any subset B of x, we define the outer measure of B to be the infimum of a certain set of real numbers. It's the set of these sums. Then let me zoom in a little bit here. It's the infimum of the set of these sums, sums of mu of ANs, where the ANs is a countable family, a sequence in fancy A, and it covers the set B, and the series converges. So that way we don't have to talk about infinity. So the outer measure of B is the infimum of a certain set of real numbers. And we've argued that this is a non-empty set that is bounded below, partly non-empty, partly thanks to the fact that we require x to be in there. Okay, and I think one reason that I've had a lot of trouble verbalizing, I don't have trouble writing things down, but I have trouble verbalizing sort of and explaining out loud what's going on. I think one cause for that is that I don't have a nice name for this set of numbers, so I keep referring to it in awkward ways. So let's just give it a name. Let's just define, for any B subset of x, let's give the set of numbers a name. What should we call these numbers? I propose that each of these numbers be referred to as an approximation from above of the size of B. From above, since it's considering covers of B, and it's sort of using addition to approximate the measure or the size of B. So how about this notation? Approximations, the set of approximations from above of B will be this. So that's a certain set of real numbers, and then I can just say, okay, the outer measure of B is defined to be the infemal approximation from above of B. It's the infimum of the set of approximations from above. All right, that should make it easier to talk a little bit through proofs. All right, onward to the proof of this lemma.